In our discussion of Heilbronn logic, we assume that there is a one-to-one relationship between ground terms in our language and objects in the application area we're trying to describe. For example, we assumed a unique name for each person. In arithmetic, we often assume a unique term for each number. This is often called an isomorphic representation because there is a one-to-one relationship from the ground terms in our language onto objects in the world. This makes things conceptually simple, and it's a reasonable way to go in many circumstances, but not always. In natural language, we often find it convenient to use more than one term to refer to the same real-world object. For example, we sometimes have multiple names for the same person, like Michael and Mike. And in elementary arithmetic, we frequently use different terms to refer to the same number. 2 plus 2, 2 times 2, s of s of s of s of 0, and so forth. The reverse is also true. We sometimes find that there are objects in an application area for which we have no names at all. For example, we have names for many real-world numbers, real numbers, integers, decimal numbers, and some transcendental numbers like pi and e. However, we do not have names for all of them because we have only countably many names and uncountably many numbers. Heilbronn semantics is also problematic when we want to define functions and relations in a general way that applies to worlds with differing numbers of objects. For example, we might want to state the fact that addition is commutative, whether we're considering finite arithmetic, arithmetic over the natural numbers, or arithmetic over the real numbers. Unfortunately, we cannot do this in Heilbronn logic since it requires that we fix the language and therefore the number of objects in advance. First-order logic is an extension to Heilbronn logic that deals with these problems. In many ways, it's similar to Heilbronn logic. The syntax of the two languages is almost identical, and the proof method is almost the same. The main difference is in the semantics. We start this lesson by introducing the idea of a conceptualization. It's a mathematical structure consisting of a language-independent universe of objects, together with functions and relations on that universe. Then we define a semantics that gives meaning to sentences without fixing in advance the universe of objects. We present a selection of examples. We develop a proof system for first-order logic. And finally, we present some sample proofs.